When a solid object breaks, it rarely happens in a single, unexplainable instant. Long before a catastrophic failure, a complex, invisible struggle takes place deep inside the material as its atomic bonds fight to resist an external force. To expose that struggle, engineers use a standard tensile test. They take a metal cylinder or a thick wire, clamp it down, and use an industrial machine to slowly pull it apart from both ends. To map exactly what happens inside the metal, we plot a chart. The y-axis tracks our first critical metric, stress. This is the internal restoring force developing inside the material per unit area as it tries to hold itself together. The x-axis tracks the physical consequence of that force, strain. Strain is simply the fractional change in the material's length compared to its original size. As the machine increases the pulling load, we plot a line matching the rising stress against the resulting strain. This records the metal's exact behavioral response in real time. Eventually, the applied force becomes too much for the material to distribute evenly. The center of the wire begins to rapidly thin out and narrow, a physical warning sign known as necking. And then the internal atomic bonds completely fail. The metal violently snaps. If we want to know exactly why and when that wire gave up, we have to rewind the test and learn how to read the physical history recorded right here on this curve. Let's look at the very beginning of the material's journey. Starting from zero applied force, the curve plots upward in a perfectly straight, diagonal line from the origin to a marker we'll call point A. This straight line illustrates Hooke's law. In this specific proportional region, the stress and strain are in exact lockstep. If you remove the load anywhere along this line, the metal behaves like a perfect spring and bounces back to its exact original dimensions. But if we keep pulling, the curve extends slightly past point A and begins to flatten out, hitting a critical marker, point B. This is the yield point, or the elastic limit. The specific amount of stress required to reach this tipping point is known as the material's yield strength. For structural engineers, this number is the absolute maximum limit for a safe design. Once you cross that precise yield point, you leave the realm of safe, elastic absorption. The material is now taking on permanent, irreversible damage. As the load increases past the yield point, we enter a zone of rapid deformation. Notice how the curve bows outward significantly, heading up toward a high peak. This phase is called plastic deformation. If we stop the machine and remove the load right here at point C, the material will never shrink back to its original length. It now has a permanent set, represented by this remaining strain even when the stress drops back to zero. Eventually, the curve reaches its absolute highest peak. This is point D, the ultimate tensile strength. It is the absolute maximum stress the material can endure. Beyond this peak, the material is actively ginning up. Even if we reduce the pulling force, the internal structure is already unraveling, and additional strain is produced with less effort. The line drops slightly and abruptly terminates at point E, the fracture point. The metal has officially broken. Everything plotted from the yield point at B to the fracture at E serves as a comprehensive map of structural failure. It's a sequence mechanical engineers spend their entire careers analyzing so they can avoid ever reaching it. We can actually classify different types of materials simply by looking at the physical gap between their ultimate strength and their final fracture point. Take a look at this curve, where the ultimate strength peak and the fracture point are stacked closely together. This indicates a very brittle material, like glass, which suddenly shatters almost the second it hits its maximum capacity. Now compare it to this overlaid curve, where the fracture point is stretched far to the right. This represents a highly ductile material, like copper, which will stretch and deform significantly before it finally snaps. Engineers use this comparative data to make life-or-death design choices, knowing exactly how much a material will bend before it breaks. Up to this point, we've mapped the predictable, rigid rules of metals and building materials. But there is a class of materials that completely ignores this standard linear graph. They are called elastomers, and you have them inside you right now. Think about the elastic tissue of the human aorta, the massive vessel responsible for carrying blood away from your heart. If we plot the aorta's behavior, the chart looks completely different. We get a sweeping, nonlinear exponential curve that stretches massively along the strain axis, without ever marking a clear, defined yield point. This biological tissue doesn't obey Hooke's law. There is no perfectly straight proportional region at the beginning, and it lacks a well-defined plastic zone. Evolution designed it this way out of sheer necessity. To keep you alive, human heart tissue must stretch to several times its original length and perfectly return to shape millions of times over a lifespan without ever taking on a permanent deformation. When human beings build, we rely on the mathematical predictability of yield strengths. We need steel beams and massive concrete columns to hold firm, resist stretching, and stay well below their elastic limits. Biology requires the exact opposite. For a skyscraper, or trying to understand the beating of a human heart, the stress-strain curve provides a precise physical autobiography of how matter survives under pressure.